Our second slide set in this module 4 then takes us into wind. So wind is the condition of moving energy and sometimes matter from a high pressure scenario to a low pressure scenario, and everything succumbs to this basic physics principle. So most of us want to get out of high pressure environments and be in low pressure environments, and the atmosphere is not any different. And the condition is that the atmosphere wants to find equilibrium. It wants to find balance. So if we take a look at this top diagram, we've got a high pressure cell here, and we've got a low pressure cell over here. And so the movement is going to be across from the high to the low. The condition of the atmosphere wants to make both of these of the same pressure. But because the Earth is always receiving energy from the sun, we're always generating some volume of low pressure across our planet. And because we've got places with differential albedo, places like Antarctica, which are generally very light in color, which means they're going to be cooler, and they're a location where we've got descending air, which is going to result in high pressure. We're going to always be generating high pressure cells and always generating low pressure cells. So consequently, that energy and matter is going to be always moving across the planet in various conditions and locations. And consequently, then, the direction of the wind is going to change. So with that, because we move from high pressure cells to low pressure cells in the genesis of wind, we create something called a pressure gradient. Sometimes known as a pressure gradient force. And the pressure gradient tells us how fast that wind is. So if this high pressure cell isn't as dense and isn't as significantly large as this low pressure cell, then the wind is going to be rather slow. So the pressure gradient is going to be low. If, on the other hand, this high pressure cell is enormous and the low pressure cell is enormous, there's a big difference between the high pressure and the low pressure, then the amount of energy moved from here to here over this same distance is going to be greater. That pressure gradient is going to be greater, and therefore the wind is going to be greater. All right, so the steepness of the pressure gradient is going to determine how quick that wind is moving. So again, as I said, wind moves from high pressure cells to low pressure cells, and that's because this high pressure cell, in this case, the high is here, this high right here. What's happening is with those convection currents that we talked about last unit, the air is dropping and being forced to the surface of the Earth. So what we're doing is we're taking all of that mass of that atmosphere and we're pushing it at the surface of the Earth. So it would be like putting a little bathroom scale here. It's when you step on a bathroom scale, you are measuring the amount of force that all of the matter that you are made up of is exerting on the surface of the Earth at the location where that bathroom scale is. So consequently, all of this mass is pushing down on the surface of the Earth here, creating a high pressure zone. That wind is going to then move and find its way into a low pressure zone because it wants to create that equilibrium. And at this location where the low happens to be because the molecules are farther apart, or they're not moving as fast, or there's just less density, we're going to lift this air up. Because when you've got low pressure, you've got more buoyancy, and the lighter, less buoyant matter is going to move up. That's generally, as you see here, warm air rises because it's energized and lifting. Here, this air is coming from this location, so it's cooling down. Remember your adiabatic lifting and falling from last module? We're going to come across, we're going to create a space here for this wind to move into. So this space is created, and then we're going to lift. So because we're lifting, it's like stepping off that bathroom scale. It's going to register 0, right? Now there's never a complete absence here. It's not like you and I stepping off of a bathroom scale and the bathroom scale isn't sensitive enough to measure the air mass. It's just measuring us. Instead of going to 0, there's still going to be a little bit of pressure exerted on the surface of the Earth by the air that's coming into this location before it begins to lift. Because that's constantly in a lifting state, we're going to have a low pressure cell here. So lifting low, high pressure is falling. So we get this rotational scenario that we introduced last unit. So the three physical forces that produce wind, we've given you the first one, which is that pressure gradient force. All right, so we're going to move from high pressure cells to low pressure cells, and I want to draw your attention to this diagram right here of Europe, where we've got a low pressure cell here, but we've got a high pressure cell sitting out over here somewhere, and a high pressure cell diagrammed right here, and I can tell by these isobars that I've got another high pressure cell here. Think of high pressure cells like you're dropping a bunch of marbles and they hit the surface of the earth. They're applying a lot of pressure right where they hit, but then they sort of roll off into multiple directions, right? And they're moving radially out towards whatever lows are closest to them or adjacent to them. So in this case, we're going to get some movement here, we're going to get some movement here, and we're going to get some movement here. All right, and so that's that pressure gradient force. And like we said, when the wind is fast, we're moving a lot of matter over a short distance. When the air is not really dense, so the difference between over here and here isn't great, then the wind is going to be slower, and then slower here as well. And you can tell that by what are called isolines. The meteorologist is going to generate the volume of pressure on the surface of the earth, and just like connect the dots where you and I, when we were kids, we were connecting the dots, and we were either connecting the dots 1, 2, 3, 4, 5, or we're counting by fives, 5, 10, 15, 20. The meteorologist is looking to connect all the dots with the same number. So each one of these lines across here is the same value. So this is going to all have the same pressure here. This line is going to have the same pressure. This line is going to have the same pressure. So as we're coming from a high pressure cell to a low pressure cell, I've got to travel quite a long distance before I see a change in pressure. So this is going to be slower wind. We've got a lot of space between these two isolines here, so this is going to be a slower wind. The lines are getting closer together here, so we know that wind is picking up in velocity. So we've got maybe a medium velocity wind here, and then if you take a look here, I've got another medium velocity wind, but the isolines are coming in closer. It's like traveling down a short set of stairs. They're really close together, so the wind velocity is picking up here, and I can tell that because these lines are closer together. So wind then moves in a perpendicular direction to the isolines. All right, so this line is coming here and it's striking this isoline at a 90-degree angle. 90-degree angle, 90-degree, 90-degree, all the way through for all of these lines. All right. So for the most part, this is how wind moves, is across these isolines. But we have to introduce the Coriolis force. The Earth is spinning, and that spinning is going to deflect those isolines. So we're not going to travel in a nice straight line. It's going to bend. And if you are unsure of how this works, do that old trick of sort of spinning out in the backyard somewhere when you were a kid. You put your arms out, you span, or you spun around and spun around and spun around, and then you stopped, and then you tried to run in a straight line, and you can't run in a straight line, right? You end up sort of curving off, and it's that same motion. You're curving because the equilibrium in your ears, all the fluid in your ears, is still rotating. The liquid force of the atmosphere is still rotating, and it would like to go straight, but it gets deflected. And we said with the Coriolis force that the deflection in the northern hemisphere is clockwise, and the deflection in the southern hemisphere is counterclockwise. So the diagram right here is showing us that all of those marbles, all that air is hitting the surface of the earth here, and then they get deflected clockwise. So they're spinning clockwise around the high, and they want to find that low, so they spin, and then they actually come into the low, and you'll see that the low is not spinning clockwise, it's spinning counterclockwise. So this condition is a North American or Northern Hemisphere scenario with a clockwise high and a counterclockwise low. Now we know low pressure cells generate clouds, so we're going to lift the air here. As we're lifting air, any moisture that's in that air is going to get lifted as well. We're going to condense out that moisture and generate a cloud, as we saw in the module ahead earlier. So I've got a lovely satellite image here of a hurricane that is coming in off of, it looks like Cuba, and you can see by the rotation it's counterclockwise. So take a look. We exited hurricane season back in November, but if you want to take a look at some old hurricane images from last season, you'll see all of them in the Northern Hemisphere rotate counterclockwise. All right, so that is the Coriolis force. That's what's happening there. Frictional forces then are going to influence the type of wind that we have in the production of wind, and frictional forces actually offer compression or expansion. It's like putting it, all that air in a little room or a big room, and it does two things. When the airspace is small, like a mountain valley, the pressure is going to be higher, so it was going to want to release that pressure, so it's going to move down those valleys real quick and then find its way into places like Kansas and Utah as it comes through different mountain environments. You and I can think of other variables with the frictional force of wind, and how that might influence the direction of that wind if we were to go for a walk or a run. If we were walking on a nice smooth paved surface, or walking on that nice smooth paved surface, we're going to basically be able to go in a nice straight line. But if we go from a paved environment to maybe a trail that has some roots and things like that that are crossing the trail, then we might find ourselves stepping over a root and then changing just a little bit the direction that we move to get over that root or to get over that log. So we're generally going in the same direction. We're still following a straight path along the trail, but our micro movements might be changed a little bit just to navigate the texture on the surface of that trail. That texture is also going to slow us down a little bit. We're going to have to pay more attention to the surface of the earth, particularly as more and more texture amounts. You're going to keep your eyes down. You're not going to travel as fast because the hazards are increasing. So we're creating a greater friction. It's creating some drag, if you will. And then instead of working through the trails that have logs and things like that, maybe you're in a boulder field and you've got these big boulders that are all over the place, and you have to navigate through these big boulders, and you can't go through a straight line. You've got to go around these. So now the direction that you're traveling, even if you want to go from point A to point B, you're going to have to go around them. So an example here would be the Alps that sort of come across this part of Europe. So the Italian Alps, the French Alps, through Germany, and then into the fracture belt here. The winds coming across Spain are going to have some topographical variation. So the wind might want to do this, but it's going to, maybe come across like this because the texture's pretty, it's starting to get a little bit more rolly through parts of Spain. But we get into France with the Alps, and now we've got these big textural features that we have to contend with. So this wind wants to get to the low, but it might end up traveling southeast for a little ways as it's finding its way down a valley, or it might end up having to move northwest for a little bit that is a northwest tending valley, but it's still going to make its way to this low. It just has to take these detours because of the frictional forces, and that those frictional forces are going to slow that wind down. I am going to take a pause here and then start the next slide.